Describe adaptive control and its uses. Definition and overview of adaptive control. Adaptive control. An adaptive control system is defined as a system whose parameters automatically change in response to changing process characteristics. This automatic change allows the system to compensate for variations in process behavior, maintaining stability and optimal performance despite load upsets and other disturbances. Benefits of adaptive control. Maintaining stability. Adaptive control systems can adjust their parameters to maintain constant loop gain, ensuring stable operation under varying conditions. Optimal response. By adapting to changes in the process, these systems provide an optimal response of the controlled variable, improving overall process performance. Beyond linearization. Adaptive control goes beyond simple linearization, which adjusts for constant steady-state gains by dynamically adjusting parameters to meet changing process requirements. Comparison with non-adaptive control systems. Non-adaptive systems. These systems have fixed parameters and may not respond effectively to changing process conditions, leading to instability and suboptimal performance. Adaptive systems offer the flexibility to adjust control parameters automatically, providing a robust solution to handle process variations and maintain desired performance. Describe approaches to adaptation. Programmed adaptation. Programmed adaptation involves setting up a program that adapts controller adjustments based on changes in process variables, such as the set point. This approach is useful for large capacity processes like heat exchangers or critical level applications where dynamic gains vary with load. Example of programmed adaptation using process variable information. A detailed investigation of a level application where the process gain varies with load. By defining the relationship between load and gain, a computer can be programmed to adjust PID settings to maintain optimal response despite changing conditions. Feed-forward adaptation. Feed-forward adaptation, an approach based on changes in load rather than process variables. This strategy anticipates disturbances by adjusting the control action proactively, improving response times and minimizing the impact of load changes on the process. Feedback adaptation. Feedback adaptation. Adjustments are made based on changes in the controlled variable, measurement. This approach ensures that the control system responds effectively to deviations in the desired output, maintaining stability and performance. Implement adaptive controllers. Adaptive hardware. Various types of hardware are available for implementing adaptive or self-tuning controllers. These controllers can induce load upsets to gather information or wait for natural disturbances to adjust PID settings. The choice of hardware depends on the specific process requirements and desired control performance. Examples of adaptive control implementation. Describes how adaptive control strategies have been successfully applied in the process control industry. These examples highlight the effectiveness of adaptive controllers in maintaining stability and optimizing performance in complex processes. This section provides detailed information on the definition and benefits of adaptive control, different approaches to adaptation, and the implementation of adaptive controllers using various hardware solutions. General principles of advanced control systems. Basic concepts. Basic concepts. Advanced control systems are built on fundamental control theory principles, but extend to more complex strategies and methodologies. Key components include sensors for measuring process variables, controllers for computing control actions, actuators for implementing control actions, and communication networks for data exchange. Understanding the interplay between these components is essential for designing effective control systems. Control strategies. Control strategies. Advanced control strategies encompass a range of techniques. Feedback control. Uses current measurements to adjust the process and maintain the desired output. Feed-forward control anticipates disturbances by measuring changes and adjusting the process proactively. Optimal control minimizes or maximizes a performance index, e.g. cost, energy consumption subject to process constraints. Robust control ensures stability and performance despite uncertainties in process parameters and external disturbances. Nonlinear control addresses systems with nonlinear behaviors, requiring specialized algorithms to handle their complexities. Benefits and challenges. Benefits. Advanced control systems offer numerous benefits. Improved process efficiency. Enhanced control leads to better utilization of resources and reduced waste. Enhanced safety. Precise control and monitoring can prevent hazardous situations. Reduced operational costs. Optimization of processes can lead to significant cost savings. Challenges. Implementing advanced control systems also presents challenges. Complexity. Designing and tuning these systems require deep technical expertise. Maintenance. Advanced systems may require more frequent and specialized maintenance. Integration. Compatibility with existing systems and processes can be a hurdle. Advanced control system types. Model predictive control. Model predictive control, MPC. MPC uses a dynamic model of the process to predict future behavior over a defined horizon. By solving an optimization problem at each control step, MPC determines the control actions that will optimize process performance while adhering to constraints. Key features include prediction model, a mathematical representation of the process dynamics, control horizon, the future time period over which predictions are made, optimization, an objective function is minimized or maximized, often considering constraints like actuator limits and safety margins. Receding horizon. As each control step is implemented, the horizon moves forward in time. Adaptive control. Adaptive control. These systems continuously adjust their parameters to accommodate changing process dynamics, ensuring optimal performance. Techniques include self-tuning regulators, STR, adjust controller parameters in real time based on process measurements. Model reference adaptive control, RAC, adjusts controller parameters to match the behavior of a reference model. Gain scheduling changes controller gains based on operating conditions or measured variables. Multivariable control. Multivariable control manages processes with multiple interacting variables using techniques like decoupling, minimizes interaction between control loops by designing controllers that negate the effect of one variable on another. Relative gain array, RG, a tool to analyze and quantify the interaction between control loops, aiding in the design of effective multivariable control strategies. Robust control. Robust control ensures system stability and performance despite uncertainties. Techniques include H-infinity HB control, optimizes the worst-case performance, providing a guaranteed level of robustness. Mu synthesis designs controllers that handle structured uncertainties in the process model. Nonlinear control. Nonlinear control addresses processes where linear control theories are insufficient, using methods like feedback linearization. Transforms a nonlinear system into an equivalent linear system through state and control transformations. Sliding mode control uses discontinuous control actions to drive system states to a desired sliding surface and maintain them there. These sections delve into the technical aspects of advanced control systems, providing a deeper understanding of their principles, strategies, and types, along with specific methodologies and techniques used to achieve effective control in complex processes. Applications of advanced control systems. Process industries. Process industries. Overview of the implementation of advanced control systems in various process industries. This section highlights how these systems improve operational efficiency, product quality, and safety in industries such as refining, food processing, and pharmaceuticals. Chemical and petrochemical. Chemical and petrochemical. Detailed discussion on the use of advanced control systems in chemical and petrochemical plants. This includes optimizing reaction conditions, managing complex separation processes, and enhancing the overall plant performance through real-time adjustments and predictive analytics. Oil and gas. Application of advanced control systems in upstream, midstream, and downstream oil and gas operations. This section covers reservoir management, drilling optimization, pipeline monitoring, and refining processes, emphasizing the role of advanced control in improving yield, safety, and environmental compliance. Power generation. Power generation description of how advanced control systems are used in power plants to optimize the generation and distribution of electricity. This includes load forecasting, boiler control, turbine optimization, and integration of renewable energy sources to ensure reliable and efficient power supply. Other industries. Other industries. Exploration of advanced control applications in diverse industries such as automotive, aerospace, and manufacturing. This section provides examples of how these systems enhance process control, product quality, and operational efficiency across various sectors. Implementation and management of advanced control systems. System design. System design. Key principles and best practices for designing advanced control systems. This includes defining control objectives, selecting appropriate control strategies, and designing the control architecture to meet specific process requirements. Software and hardware requirements. Software and hardware requirements. Detailed information on the software and hardware components necessary for implementing advanced control systems. This section covers the selection of controllers, sensors, actuators, communication networks, and control algorithms to ensure system reliability and performance. Integration with existing systems. Integration with existing systems. Guidelines for integrating advanced control systems with existing control infrastructure. This includes interfacing with legacy systems, ensuring data compatibility, and maintaining operational continuity during the transition to advanced control. Maintenance and troubleshooting. Maintenance and troubleshooting. Strategies for maintaining advanced control systems to ensure long-term reliability and performance. This section covers routine maintenance tasks, diagnostics, and troubleshooting techniques to address common issues and minimize downtime. Training and support. Importance of training and support for successful implementation and operation of advanced control systems. This includes developing training programs for operators and engineers, providing ongoing technical support, and ensuring knowledge transfer for effective system use and maintenance. These sections provide comprehensive guidance on the applications of advanced control systems in various industries, as well as detailed information on the design, implementation, and management of these systems to achieve optimal performance and reliability. Successful implementations, a collection of case studies demonstrating the successful application of advanced control systems in various industries. Each case study details the specific challenges faced, the solutions implemented, and the outcomes achieved, highlighting the tangible benefits of adopting advanced control technologies. Chemical industry. Example of a chemical plant that implemented Model Predictive Control, MPC, to optimize reaction conditions, resulting in improved yield and reduced energy consumption. Oil refinery. Case study of an oil refinery that adopted multivariable control to manage complex distillation processes, leading to enhanced product quality and increased throughput. Power plant. An illustration of a power generation facility that utilized robust control systems to integrate renewable energy sources, ensuring stable and efficient power supply. Lessons learned. Lessons learned. Insights and takeaways from the case studies, focusing on the key factors that contributed to the success of the implementations. This section discusses common challenges, best practices, and strategies for overcoming obstacles in the deployment of advanced control systems. Effective planning. Importance of thorough planning and stakeholder engagement in the success of control system projects. Customization and flexibility. Need for tailored solutions that fit the specific requirements of each process and the flexibility to adapt to changing conditions. Training and support. The critical role of training and continuous support in ensuring the long-term success and sustainability of advanced control systems. Future trends in advanced control systems. Emerging technologies. Emerging technologies. Exploration of new and emerging technologies that are shaping the future of advanced control systems. This includes advancements in artificial intelligence, AI, machine learning, and big data analytics that enhance the capabilities of control systems. AI and machine learning. Integration of AI and machine learning algorithms to improve predictive accuracy and optimize control strategies dynamically. Big data analytics. utilization of big data analytics to process large volumes of data, providing deeper insights into process behavior and enabling more informed decision-making. Industry 4.0 and IoT. Industry 4.0 and IoT. The impact of Industry 4.0 and the Internet of Things, IoT, on advanced control systems. This section discusses how connectivity and smart devices are transforming control systems, making them more intelligent, autonomous, and interconnected. Smart sensors and actuators. Development of smart sensors and actuators that provide real-time data and diagnostics, enhancing the responsiveness and accuracy of control systems. Cyber-physical systems. Integration of cyber-physical systems that combine physical processes with digital control, enabling more sophisticated and adaptive control strategies. Future research directions. Areas of ongoing and future research in advanced control systems, focusing on addressing current limitations and exploring new opportunities for innovation. Resilience and security. Research into enhancing the resilience and cybersecurity of control systems to protect against disruptions and cyber threats. Sustainability. Development of control strategies that promote sustainability, such as energy-efficient processes and reduced environmental impact. Human-machine collaboration. Investigation of new ways to improve human-machine collaboration, ensuring that control systems are user-friendly and that operators can effectively interact with and manage advanced control technologies. These sections provide a detailed look at successful implementations of advanced control systems, the lessons learned from these experiences, and the future trends and research directions that are shaping the evolution of advanced control technologies. Cascade control. Supply upsets refers to disturbances or changes in the supply conditions that can affect the process controlled by a cascade control system. Understanding and managing these upsets are critical for maintaining stable operation. Supply upset summary. Supply upset summary. A brief overview of the impact of supply upsets on cascade control systems, including typical responses and adjustments needed to maintain control performance during such disturbances. Simplified block diagrams of cascade. Simplified block diagrams. Visual representations of cascade control systems, illustrating the relationship between primary and secondary loops. These diagrams help in understanding the basic structure and interaction of components in a cascade control setup. Properties of the secondary loop. Secondary loop properties. Characteristics of the secondary loop in a cascade control system, including its role in regulating intermediate variables to achieve desired set points in the primary loop. Key properties include response time, control actions, and interaction with the primary loop. Summary of results and considerations. Results and considerations summary. A summary of the outcomes and key factors to consider when implementing cascade control. This includes performance benefits, typical challenges, and considerations for optimizing cascade control systems. Advantages of Cascade. Cascade advantages. Benefits of using cascade control systems, such as improved response times, reduced process variations, and enhanced stability. Cascade control allows for more precise regulation of complex processes by controlling intermediate variables. Limitations of Cascade. Cascade limitations. Drawbacks and limitations of cascade control systems, including potential complexity, increased tuning requirements, and the need for accurate secondary loop control. Understanding these limitations helps in designing and implementing effective cascade control strategies. This section provides a comprehensive overview of cascade control, including its structure, advantages, limitations, and considerations for managing supply upsets and tuning the system effectively. Specific cascade applications. Valve positioner, a common application in cascade control where a positioner acts as a high-gain proportional controller. The positioner helps eliminate valve hysteresis, ensuring precise control by accurately positioning the valve based on the controller's output. Liquid flow or liquid pressure on valve position cascade. Liquid flow pressure cascade. Application of cascade control involving liquid flow or pressure loops with a valve positioner as the secondary loop. This setup helps manage fast processes by ensuring the valve responds accurately to flow or pressure changes. Limit cycling. Limit cycling, a phenomenon where the controlled variable oscillates with a constant amplitude, often caused by hysteresis or deadband. Recognizing limit cycles helps in diagnosing and correcting tuning issues to achieve stable control. Temperature on flow cascade control. Temperature on flow cascade. Cascade control application where temperature control is achieved by manipulating the flow of a heating or cooling medium. This setup is effective for processes requiring precise temperature regulation, such as heat exchangers. Temperature on temperature cascade control of an exothermic reactor. Temperature on temperature cascade, a specialized application in exothermic reactors where the temperature of the reactor is controlled by adjusting the temperature of the jacket. This method ensures stable reactor temperature by managing the cooling medium's temperature. Flow as the inner loop. Flow as inner loop, using flow control as the secondary loop in cascade systems. This approach benefits from the fast response of flow loops, providing stability and improved control in primary processes. Level on flow, valve positioner cascade, level on flow cascade. Application of cascade control for liquid level regulation using a valve positioner as the secondary loop. This method is effective for maintaining precise level control in processes with frequent supply or demand variations. Integral wind-up preventing measures in cascaded loops. Wind-up or saturation. Wind-up saturation occurs when the controller output exceeds its limits, causing the integral term to continue accumulating error even when the actuator is saturated. This leads to loss of control and instability in the system. Wind-up prevention measures. Wind-up prevention. Techniques to prevent integral wind-up, such as placing the controller in manual mode, using batch controllers, implementing external feedback, and applying digital algorithms. These measures ensure the controller remains effective within its operational range. Causes of wind-up in cascade. Causes of wind-up. Situations that lead to wind-up in cascade systems, such as breaks in the cascade loop or manual operation of the secondary controller. Identifying and mitigating these causes is essential for maintaining stable control. External feedback to prevent wind-up in cascade. External feedback, a method to prevent wind-up by providing an external feedback signal to the integral term of the controller. This ensures the controller output remains within its operational limits, preventing saturation and maintaining control stability. These sections provide detailed information on specific applications of cascade control and measures to prevent integral wind-up, ensuring effective and stable control in various industrial processes. Tuning cascade loops to specific performance criteria. Order of start, the sequence for initiating and tuning cascade control loops. The secondary loop should be tuned first before integrating it with the primary loop. This ensures the secondary loop is stable and responsive before it affects the primary control loop. Common cascade pairs. Common cascade pairs, typical pairings of primary and secondary loops in cascade control systems, such as temperature control with flow as the secondary loop, or level control with valve position as the secondary loop. These pairs leverage the strengths of each loop to achieve optimal control. General tuning considerations. General tuning considerations. Guidelines for selecting and tuning control modes in cascade systems. Secondary loops are often tuned using proportional or proportional plus integral control modes, while primary loops typically use PI or PID controllers. The tuning process aims to achieve a balance between responsiveness and stability. Improved performance over a feedback loop. Improved performance. Cascade control systems often outperform single feedback loops by providing faster response times and reducing integrated absolute error, IAE. The secondary loop quickly corrects disturbances, preventing them from affecting the primary loop and improving overall control accuracy and efficiency. This section outlines the procedures and considerations for effectively tuning cascade control loops to achieve specific performance criteria, ensuring stable and optimal operation in various industrial processes. Define selectors used in analog and digital applications. High selectors. High selectors, devices or software blocks that select the highest value among the measured variable inputs. The highest value is passed through and the unselected inputs are dead-ended. High selectors are used to ensure that the most critical measurement, highest value, controls the process. Low selectors. Low selectors, devices or software blocks that select the lowest value among the measured variable inputs. The lowest value is passed through and the unselected inputs are dead-ended. Low selectors are used to ensure that the process is controlled by the least critical measurement, lowest value. Median selectors. Median selectors, combinations of high and low selectors that select the median, middle value among three inputs. The highest and lowest inputs are dead-ended, and the median value is passed through. Median selectors are used to provide a balanced control by excluding extreme values. Analog hardware versus digital. Analog hardware versus digital. Comparison of analog and digital selectors. Analog selectors provide smooth transitions between input signals with minimal noise and dead band. Digital selectors, often more flexible, allow for configurable selection capabilities without additional hardware costs. The choice between analog and digital depends on the application's requirements and constraints. Describe basic selective control loop applications. Protection against instrument failures. Protection against instrument failures. Selective control schemes to prevent process shutdowns due to instrument failures, typically occurring in hostile environments with vibration, corrosion, or high temperatures. Redundant instrumentation and selector systems ensure continuous operation despite individual instrument failures. Furnace pressure measurement protection. Furnace pressure measurement protection. Application of median selectors in furnace pressure measurement to maintain proper draft pressure and prevent catastrophic implosions. Redundant pressure transmitters and median selectors ensure stable furnace operation by mitigating the impact of transmitter failures. Exothermic reactors. Exothermic reactors. Use of high selectors to manage the catalyst flow in exothermic reactors. In case of transmitter failure, the high selector ensures safe shutdown or continued operation by selecting the highest valid measurement, preventing unsafe conditions. Control through most critical measurement. Control through most critical measurement. Selective control schemes where the process is provided with multiple measurements, but only the most critical measurement controls the process. This auctioneering strategy ensures the highest priority variable dictates the control action, enhancing process safety and efficiency. Protection of equipment, safety, parallel metering combustion scheme, a selective control application in boiler systems to maintain safe furnace conditions, pressure, and air-fuel ratios. The cross-limiting arrangement of selectors ensures safe operation by managing fuel and air flows in response to load changes. Pumping station on a pipeline. Application of selective control to protect pipeline pumping stations from cavitation, motor overload, and overpressure. Selectors ensure that the most critical condition, e.g., lowest suction pressure, highest motor load, governs the control action, protecting the equipment from damage. These sections provide detailed information on the types of selectors used in analog and digital applications and describe basic selective control loop applications, focusing on instrument failure protection, critical measurement control, and equipment safety in various industrial processes. Protect the selective control strategy from wind-up and tune to an acceptable criterion. Wind-up protection. Wind-up protection. Wind-up occurs when the integral action of a controller continues to integrate error during periods when the control action cannot influence the process, leading to large overshoots when normal operation resumes. This phenomenon can destabilize the control loop and degrade performance. External feedback as wind-up protection for selective loops. External feedback. In selective control applications involving multiple controllers, only one controller's output manipulates the control element at any given time. To prevent wind-up in the unselected controllers, an external feedback connection is employed. This feedback ensures that the integral action of the unselected controllers does not accumulate excessive error, effectively turning them into proportional controllers while they are not in control. Tuning selective loops. Tuning selective loops. The tuning process for selective control systems requires treating each loop as an individual feedback loop. During the tuning of one loop, other loops are placed in manual mode and their outputs driven beyond the selection range to isolate the loop being tuned. This approach allows each loop to be tuned using standard methods to achieve desired response characteristics. After tuning, the system is tested to ensure smooth and bumpless transfer of control between the controllers, maintaining stable and efficient operation. This section provides detailed guidance on preventing wind-up in selective control strategies and tuning selective loops to ensure stable and efficient process control.